So as we are looking at this and we're looking at what is a sequence. Sequence, if you were going to define that for me, what are we knowing about a sequence if you remember from earlier? What would someone want to say? Raise your hand. Sequence is what?
Pattern.
Pattern of what, usually? Numbers. Usually a pattern of numbers, right? So it's like a list or a pattern, and a lot of times you're going to have many, so a pattern of numbers, we could say. It's kind of like that list. And the types of sequence that we learned about earlier were called what kind of sequences? Anyone remember? Arithmetic or arithmetic, if we are looking at those. Did you find your notes? Okay. So when we think about arithmetic, we always had constant addition or subtraction. Okay? You wrote formulas both recursively and explicitly. You're going to be doing that same type of thing. So what we're going to be looking now is at what's called our geometric sequences. If we are looking at our ICANN statements, it's formed by that common ratio between pairs of terms. Common ratio means usually you're going to divide the newest number by the one previous to it. That's how you get that common ratio. So it's just dividing, if it's the fourth number in the sequence, you divide it by the third number in the sequence. The second divided by the first, that'll give you that common ratio. We're going to determine if it's linear or exponential, if we're looking at a sequence. This thing was geometric and arithmetic. Recursive and geometric formulas we're going to be looking at. And I can explain the recursive formula tells me how the sequence starts, because that's that 0 point. And then what the previous one is used to generate the next one. So again, that same kind of notation we're going to see. So on that next one down, we see arithmetic or linear sequences. These were the types that you had before. So where you had your recursive formula, which we had in that first half of the year in our final, A1, that was your first term. If you're thinking of it as an ordered pair, remember that ordered pair when you were thinking about that? That was kind of like the 1 and whatever this term is, that's the A1 term. And then this was your common difference, which when you wrote it, this is kind of like our point slope form, okay, if you remember that. This was kind of point slope. Only thing, some of you when we took the final also thought you should write it with Y. But this was the same, so A to the N, that's looking at the sequence, and the D was our slope, so the D here is also our slope, right? And then it was times like x minus x1, if we're thinking about that point slope form, and then it was plus y1. So if we think of this, this is when the first term, that was our A1. So writing it explicitly went that way. So if we are looking at this one, if we're going to write recursive and explicit for this sequence. So those 2, -2, 6, -10, -6. So if we were writing this, should have been -6, -10, -14. So if we are writing this one, I would like you right now to try and write your recursive. You could have had the -4 and -1 with the +2. It's easiest to write, I think, because you know this form, because you know the first term. This is the first term, that goes back here. This is the -1 because it's the first term over here, right? So that's where that 1 comes from, is down here, and the 2 comes from here. If you wanted to write it in slope-intercept form, this is when you know the 0 term, right? So the 0 term, if we would have kept going, instead of going back 4, you add 4, you would have had the 0 term being 6, right? So our 0 term is 6. That's how they got this formula. Usually, most of you did it this way, but that's how they got both of those. So, again, when we do geometric, on the top of the next page, geometric sequences. Geometric or exponential are sequences in which you multiply each term by a constant ratio or a constant multiplier. You get the next one. So, instead of A, they use G because it's geometric. So G to the N is the nth term. G to the 0 is your initial value. So that's kind of like our y-intercept. When we were looking at it, that was our A in our formulas. our g to the 1 is the first term, n is the nth term, and r is our constant ratio or our multiplier. So if we know something's doubling, that means r is going to be 2. If we know, so when you're looking at those, it says, so which one, you choose which one depending on the information given, right? So if we are looking at this, if you're given your first term or if you're given the initial value, so that kind of helps you decide how to do this. So the recursive formula, when we look at it, so that's our explicit, can be written two ways, just like our explicit for arithmetic could be written. This one, you're going to have your first term, then you'll have the rate, whatever that common ratio is, times g to the n minus 1, and you'll always put it with greater, where n is greater than 1. So looking at this page, we now want to write. So first thing, on this next one down, it says, which sequence best describes one in which the first term is 6 and the constant multiplier is -2? Okay, so if we are looking at it. So first term is 6, looks like all of them. Multiplier -2, definitely can't be this one, right? Looks like it could be here, but now if I take -3 times -2, do I get 3 over 2? No. So if we are looking constant multiplier of -2, can it actually be this one because of the -3? No. So here it's multiplier by 2, right? And our choice should be D, if we are looking at it, right? If I take this times -2, I get -12. If I take -12 times -2, I get positive 24. 24 times -2, I get -48. So it says we want to write the first 6 terms in a geometric sequence where our ratio is 5 and the first term starts at 3. So how we're going to write this is we're going to start with g to the 1. Our g to the 1 is what term? Equal to 3. G to the n, right, is equal to our ratio, 5, if you look up above, times g to the n minus 1. So this is kind of first, if we're writing it, if we're thinking this is our recursive formula for n greater than 1. So I now want to write, so that's my recursive formula. I now want to write what are those 6 terms. So g to the 1, we already knew that was 3. G to the 2 is going to be 15. G to the 3, we're taking the previous term, 15 times 3, which gives us, not times 3, times what? My mistake, times 5. Okay, so each time you're taking it times 5, so we should have had 75. G to the 4, we're going to have 75 times 5. So making that list, okay? And they asked us to do the first 6 terms. So we have 1, 2, 3, 4. We got to have 5 and 6. So g to the 5, 1365. What do we have for g to the 4? 75 times 5 gave us how much? 375. Our last one, g to the 6, taking 1365 times 5 is going to give us 1875. And our last one, 1875 times 5. So we can see that this is increasing quite quickly, right? We don't necessarily want to do a graph of this, right? If we are looking at making this graph, we definitely growth, and the growth is pretty big. It's at 5 if we are looking at that, okay? So, top of the next page, you're going to see something like this, problems in your homework. And it says find a term. So find the 5th term in the geometric sequence. The 5th term is 140. So this is what we know. We know g of 5 is equal to 140. And the constant multiplier, r, is equal to 2. So it says find the 6th term. So because we know our 5th term if we are looking at this, is 140. We only have to do what to get the sixth term? Take 140 times 2, right? So we take the previous one times 2, and in this case we should have 280. It then says, what's your first term? So if I'm going to have my fourth term, I'm going to take 140 and divide it by what? Divide it by 2, right? If I'm looking at that, that gives me 70. That's my fourth term. Does that make sense? Mm-hmm. My third term would be taking that 70 and dividing it by 2. So I could have 35. G to the 2, taking 35, dividing it by 2. Okay? And when I get that, I get our 17.5 and 17.5. If I'm looking at G to the 1 divided by 2 gives us 8.75. When you are working with these, sometimes the explicit or recursive, this is kind of doing it recursively. If we would have thought about our explicit formula, sometimes you can just substitute in and look at those, so we'll look at that another way also. So this one, you're going to have your investment as you are looking at this. So $2,000 invested at 6% compounding annually. Is there a way to express the situation in geometric sequence? To do this, we either need the first term or the initial term. So when we are thinking about this, we're going to do the first term going here, okay? We're going to do the initial term, that formula here. So we're going to do it both ways. So it says depending on which formula you want to use, you also want to use that constant multiplier. So G to the n equals our first term, G to the 1, okay, times R to the n minus 1. So this, when we think of this, this is our investment after 1 year. So is it going to be 2,000? No. So in this case, we actually have to take 2,000 times 1.06, right? Because our rate is going to be 1 plus the 0.06. Okay? So if we're using this formula, which to me, I would probably go initial value almost all the time, but I just want to show you how this one is. So we're going to take 2,000 on your calculator times 1.06. That's the number that we want to use. Times 1.06 to the n minus 1. When you took 2,000 on your calculator times 1.06, 2,120. To me, if I'm looking at this, finding the nth term, I think it's much easier to go with the initial G to the 0 times R. And in this case, we're just losing the n term. So when you use the first term here, you have to have n minus 1. When you use the nth term, you can use n up here. So G to the n is looking at, this is our initial investment. That's our initial investment. So to me, much easier because we're given that in our problem. Our rate, still adding that 1 plus 0.06, so 1.06, and to the nth power. I think this one's much easier. It's how most of your problems, the information that they give you. It's not often that I give you the first, like the year after in the problems, but just so you know how to write it both ways. Okay? So we're taking a look at our car. We want to write the formula for it, and if we are looking at this one, this is kind of our explicit formula to find the value of the car. So G to the n is going to equal, how much did our car start with the value? 22,000. It is decreasing by 12% a year. That means I'm taking 1 and I am subtracting 0.12, which gives us 0.12. 0.88 to the nth power. We want to know after 5 years. So on the test, you'll see questions very similar to this. You'll write it first like this and in your homework, and now you're going to replace the n with 5. So please do that and put it in your. So we're looking at 8 for our a to the 1, or g to the 1, excuse me. G to the 1 is 8. Does it matter if you use a? No, you can use any letter, but usually. And then we are looking at that we are taking, and what's happening each time? Okay, but we want to use it as a multiplier, so we want to say multiplying either by 0.5 or a half if you're doing it. So I don't care if you use 1/2 here, or if you write g to the n is equal to 0.5 times g to the n minus 1. This is just telling us the previous term, and you still want to keep this part, right? You don't want to say divide by 2. It's always a multiplier that we are looking for, okay? And dividing by 2 is the same as multiplying by a half. So explicit formula. You're going to start with your g to the n. So we're going to start with our g to the n. They gave us our first term, so we're going to have 8 times a half to the n minus 1 in this case. So 8 to the 0.5. And if we are looking at that, we're going to have to the n minus 1. So how do you know if you did it right? Okay, so let's put in 1. If n is equal to 1, hang on. If n is equal to 1, you're going to go to this formula and you're going to put in 8. So g to the 1 has to be 8 times 0.5 to 1 minus 1. 1 minus 1 is 0. So 8 to the 0.5 to the 0 power. 0.5 to the 0 is 1. Does it give us 8? So now we check our second term. Or maybe you check your third term, right? If we go to our third term. If we are looking at our third term, we're going to have 8 times 0.5. You're going to put in 3 for n. So 3 minus 1 gives us 2. Put this in your calculator. 8 times 0.5 to the second. Does it give us our value of our third term, which is 2? So that's how you can check if you have your formula right. Just like you could check when we did our arithmetic sequences, you can check it by plugging in your values and see if it works. Okay? So this last situation. A ball is dropped from a height of 50 feet. It bounces to 90% of its previous height. After each bounce, it says let h of n, should have been, be the height after n bounces. So explicit formula. Okay? So we are looking at h of n. So if we are starting, we want to start with h to the 0 times r. And if we are looking at that, we want to have to the n minus 1, right? If we are going with our 0 term, okay? So if we are going with our 0 term, we are going to have, in this case, n minus 1 for this one. So I want you to think about that. This is initially where it started, right? So this is the 50. This is like we haven't bounced the ball yet. After the first bounce, you are looking at g to the n equaling 50 times 0.9. It's going to bounce up quite high, right? To the n minus 1, if we are looking at that. So if we are checking that, after the first bounce, it should have been how much? 50 times 0.9, if we are looking at it. So when it is 0, right, we're looking at our 0 term. This should be n. This should be n, excuse me. Should be n. So if we go 50 and we're going to put in, this is our 0 term, right? After one bounce, where are we at? We're going to be down at 45. After our next box, so we can plug in 1, right? We can plug in 2, we can plug in 3 for each value here. Our recursive formula, g to the 1, if we're doing it that way, is 45, right? And they use h to the n. H, if we are looking at that, so h to the 1 is 45. What is h to the n equal to? Our recursive is 0.9, that's our ratio, times g to the n minus 1, where n is greater than 1. And then this one says, well, what's after the 10th box? Which formula do you think is easier to use, explicit or recursive? Definitely explicit, so we're going to find the height after the 10th box, so h of 10. We are taking 50 times 0.9 to the 10. You start 50 feet off your building, h to the 10 is equal to 50 times 0.9 to the 10th power. We're down to how many feet? 17.4. And usually we can round that to the nearest half foot in this case if we are looking at that. Okay. So as we are looking at your homework tonight, I want to look at last night's homework first. And then if there were a few questions, we will look at those.